know about chemical reactions, atoms, elements, and compounds, and other things come together to react to form other atoms, elements, and compounds. What we don't know, however, is how fast these reactions occur and why. Have you ever wondered what affects the rate of a reaction? Then stick around, because we have the answer for you.
Val the Science Gal.
Go.
Val the Science Gal. Val the Science Gal.
Science rules.
Val the Science Gal.
Inertia is a property of matter.
Val the Science Gal.
T minus 7 seconds.
Val the Science Gal.
Hi, I'm Val the Science Gal, and this episode is all about kinetics. Kinetics is the branch of chemistry concerned with the speed and the mechanisms of a reaction. Wait, what? You heard me. Let's go to Lil to find out more.
The term rate refers to the speed of a reaction. A reaction, however, is only as fast as its slowest step.
But how do you determine the slowest step?
That's what a reaction mechanism is for. A reaction mechanism is a series of smaller reactions by which the overall reaction occurs.
Consider the reaction. In this reaction, nitrogen dioxide and carbon monoxide do not immediately come together in order to form nitrogen monoxide and carbon dioxide. Instead, a series of smaller reactions come together or add up in order to form the larger reaction. Reaction mechanisms for the overall reaction are NO2 plus NO2 yields NO3 plus NO. And the second reaction mechanism is NO3 plus CO yields NO2 plus CO2. Using the concepts of Hess's law, you can cancel out the NO2s and the NO3s. This leaves you with the overall reaction of NO2 plus CO yields NO plus CO2. Go.
What does this have to do with kinetics?
See, now that you have the two mechanisms, you can determine which is the slower step, and therefore the overall rate of reaction. Which do you think is the slower step?
I don't know. The second one?
Why do you think that?
Because first is the worst and second is the best.
No, in this case, it's actually the first one.
Oh, so what's next?
I guess we know who's the slowest step here.
Hey!
Time for the next lesson. Before we can further talk about kinetics and what affects the speed of a reaction, we first need to talk about the things necessary for a reaction to occur in the first place.
This means we need to discuss collision theory, activation energy, energy diagrams, and catalysts.
This episode is brought to you by kinetics. Keeps you moving!
Collision theory. Collisions must occur in order for a reaction to occur. After all, collisions are what allow the atoms to interact and react. However, only some collisions will produce a reaction, and this is partly because of the orientation of the molecules when they collide. Let's look at an example.
Go.
In the reaction 2NO plus 2H2 yields N2 plus 2H2O, the hydrogen atoms need to collide with the oxygen in the nitrogen monoxide. When this happens, the water will form. Also, it will release the nitrogen atoms into the system, which will then combine to form the N2. To see how this works, let's go see Mallory and Lillian in the field.
I'm N.
I'm L.
We're H2!
I'm
Energy diagrams are important to kinetics because they map the change in energy over the course of the reaction. The x-axis represents the reaction time, while the y-axis represents the change in energy over the course of the reaction. Towards the beginning of the diagram, on the left side, we have the starting energy of the reactants, and on the right, we have the ending energy of the products. As you can see here, this hump represents the activation energy, which is the minimum amount of energy required for the energy to occur. If the reactants cannot overcome this energy, or if there is not enough energy in the system, the reaction will not occur.
If I'm understanding this correctly, two things are needed for a reaction to occur. First, the atoms must collide with each other at certain orientations. Also, each collision has to have enough energy or the reaction won't occur. But what if the reaction requires too much energy? Will it never happen?
No, that's what catalysts are for. Catalysts are substances used to speed up the rate of a reaction without actually being consumed during the process. Catalysts give the reaction a different mechanism and a different slow step. This slow step has a lower activation energy. With this low activation energy, the reaction can occur more quickly and also can occur more frequently.
There are two types of catalysts, homogeneous and heterogeneous. Homogeneous catalysts are catalysts that are in the same state or phase as the reactants. Heterogeneous catalysts are catalysts that are in other phases or states than the reactants. Normally, the heterogeneous catalyst will be a solid.
This episode is brought to you by Kinetics. Keeps you moving!
Oh, I didn't see you. So I think we know enough information to talk about orders and rate laws. Orders refer to the exponents in the rate law equation, and they give a chemist an idea of how the concentration of the reactant affects the rate of the reaction. Rate laws are used to determine the overall speed of the reaction with a given concentration of each reactant.
Consider the reaction A plus B yields C plus D. To find the rate of this reaction, you can use the equation. The rate is equal to the constant K times the concentration of A to the X times the concentration of B to the Y. X and Y are the orders for reactants A and B. If A was a first order, then X would be 1. If it was second order, X would be 2. And if it was a zero order, X would be 0. Therefore, making the concentration of A equal to 1 and not included in the calculations.
Every reactant in every reaction has a different order and a different effect on the rate of the equation. Because of that, the label of the rate constant always changes, and you must solve for its label. So let's look at the example equation with the two reactants A and B. In this example, A has an order of 2 and B has an order of 1. So since we're solving for labels, we're going to plug in the labels of each variable into the equation. So rate has a label of moles over liters times hours, or 1 over molar hours. A and B both have labels of molarity. So when you substitute this in, you get 1 over m times h equals m squared times m to the first times k, which again is the rate constant. When you simplify this, you get 1 over m times h equals m cubed times k. You then divide by m cubed on both sides, and you're left with k equals 1 over m to the fourth times h. What this means is that the label for the rate constant is 1 over molarity to the fourth times hours.
The word kinetic comes from the Greek word kinesis, which means motion.
So I'm sure that you're sick of our lectures by now, but don't worry, we actually have a little experiment prepared for you. The experiment demonstrates how concentration of a reactant can affect the speed of a reaction, and I promise you, it's very fun and very interesting.
For this experiment, we made elephant toothpaste. However, it's not actual toothpaste, so please don't eat it. To make this, we used hydrogen peroxide, potassium iodide, dish soap, and food coloring.
The potassium iodine is used as a catalyst in this experiment. Do you remember what that is? It speeds up the decomposition of the hydrogen peroxide into oxygen and water. When the oxygen forms, it creates bubbles in the dish soap, which gives the toothpaste that foamy texture that you will see. We added the food coloring just to give the toothpaste some color, and so that will look more interesting.
We actually did this experiment twice. After looking at some data and chemical reactions, we saw that the peroxide had an order of 1. In the first experiment, we had a solution that was 30% peroxide, and in the second, we had one that was 15% peroxide. This means that the rate of the first solution was higher, twice as high, as the rate of the second solution.
Enough with the talking and enough with the lectures. Let's see some kinetics in action.
Just like atoms need enough energy in order to react, I need enough energy in order to edit this video. That's why I drink Dunkin' Donuts.
Dunkin' Donuts. America runs on Dunkin'.